Hi everyone, my name is Jianxun Lian. I am a PhD student from University of Science and Technology of China. I got a message of this contest when I was going to CIKM this year's accepted paper list. Then I found this interesting competition. Since one of my research interests is cross-domain user activity analysis, I decided to spend several days joining these games. Luckily, I won the second place, and here I will introduce my solution. This talk will mainly cover three parts. Firstly, I will go through the problem statement very quickly to make sure that new joining audience could catch up with the contest. I suggest you to skip the following three slides in case everyone here is already familiar with the competitions. Then I will spend most of the minutes on my solutions, which is consisted of three core components, namely feature engineering, negative samplings, and model selections. At last, I will make some conclusions and share some experience I have learned during the competition. Okay, let's start with the task statements. With the rapid development of smart devices, users now have various choices to connect to the internet for daily activities, such as smartphones, tablets, laptops. The trouble is that users' digital choices are highly segmented if we do not have an effective way to link the same users on different devices. To build an accurate user profiling models, especially for online advertising, it is essential to link the same users to enrich the user behavior data. So the theme of the 2016 CIKM Cup is to match the same user across different devices. Participants were provided with 4 data files. The first one contains users' browsing logs with event ID and timestamps. For each event, there is maps between the event ID and URLs, and maps from the event IDs to HTML titles. All the IDs are anonymized. The host also released parts of the matching user pairs for supervised training. The basic idea behind our solution is that a matched user pair should share some common patterns. The common patterns could be revealed through multiple dimensions, such as temporal similarities, websites, and contents. From temporal angles, some users like working or playing late at night, while some users have to get up early in the morning to go to work. From the angle of websites, some people prefer to use Bing as their favorite search engines, while some people like using Google. Users are frequently visit GitHub.com or LeetCode.com, indicating that they are programmers, while some users frequently visit video sites or game sites, indicate that they tend to have entertainment on their smart devices. However, there is no simple rules to determine that those two groups of users do not have any overlaps. The last example is from content similarity. User A frequently visits sites whose titles containing words like machine learning cafes, while user B's corpus includes financial technical terms. It is very possible that user A and B are two different people. A's major is data mining, while B majors in accounting. The problem is, given the data, what is the probability that they are the same users? That's why we need machine learning techniques to help automatically learn complicated rules from the above clues. Basically, we take the user linking problem as a binary classification problem. Given a pair of users, label 1 stands for they are matching users, while label 0 means they are not. Here, this is our working patterns. For local evaluations, we split the training data into our training sets and validation sets. Then we sample a certain number of negative instances for each user in training sets. They, together with matching pairs from the training instance for classifications, we generate features for each instance. Note that each instance indicates a pair of users. On its training instance, various classification algorithms can be used. Similarly, we build a test instance and use the local validation sets for performance tunings, and then select the best model for test dataset prediction. Next, I'm going to explain the three essential components in our pipelines. Feature engineering is here, negative sampling is here, and here is the model selection. Since feature engineering is usually the key to achieving top rankings in data mining context, we design comprehensive features based on the browsing logs. At the beginnings, we design some similarity metrics given to features. As listed in the slides, we built a document for each user, in which the sentences are the HTML titles. A document is represented in TF IDF vectors. Then we can calculate the cosine similarity between the two document vectors. Similarly, if we take event IDs or URLs as words, we can get another two types of documents. We name them with field similarity and URL similarity. We also count the number of common event IDs and common URLs. For temporal features, we first count a user's hourly or daily or monthly activity level distributions. Take the granularity of hour, for example. We count the number of events in each hour, which will result in a 24-dimension vector. Then we normalize the vector to make the sum equal to 1. For two users, their hour similarity is the Pearson similarity between the two vectors. The same goes for daily and monthly vectors. Besides Pearson similarity, we also calculate the cost entropy between the temporal vectors. There are several more features designed by Intuition, such as the gap between the first days of user A and the first day of user B, and how many days they are both active. For more detail, after design the above features, we can't wait to see the performance of the model. But after trying many times, the F1 score is low. Then we start to think that the features are not enough. As mentioned in the previous slides, we believe that some useful URLs can help distinguish users. Visiting Bing.com is commonly happening among different users, while a common visit of personal homepage strongly indicates a matching user pair. So we try to find out those key URLs. To this end, for each URL edge, we calculate the ratios of the probability that it appears it appears in a matching user pair to less in a random user pair. We name the ratio as ratio lift. And this table lists the top 10 key URLs. We can observe that These URLs are much more likely to appear in positive pairs than in negative pairs. There are about 5,000 URLs with lift ratio above 2,000. We use 7 numbers to record how many common URLs between the two candidates belong to the top 100, 1,000, and 2,000, 3,000, 4,000, and 5,000 key URLs. And just adding these 7 numbers, our F1 score increased significantly. This improvement gave us the inspirations. If we only calculate some numeric scores of similarities, many underlying messages between the two users is not well captured. So we plan to design more fun grand features. As mentioned in the last slide, we get a list of key URLs, which breaks the top 4,000 key URLs into 40 buckets. Then we use a 40-dimension vector to record how many common URLs between the two users are in each bucket. Secondly, we simply use an indicating vector to record whether each key URL has appeared in the common URLs. Due to space limitations, we cannot include too many features, so that we only record the top 500 key URLs. At last, in the previous steps, we calculate hourly or daily or monthly similarity as temporal features. Here we use the original numbers as features. Take hour for example, we keep the 24-dimension vector as features. We name all these features with footprints. We use all the 3 groups of features. We can observe a clear improvement when adding new groups of features, especially adding footprints. And this table lists the top 10 most important features according to the built-in functionalities of gradient boosting decision tree. There are more than 240,000 unique users in the training set. The complete training candidate size is 240,000 times 240,000. Now, for each instance, we already extract 621 features. We randomly output 10,000 instances and found that the file size is about 17 megabytes. In this way, enumerating the whole training candidates will require about 100 terabytes. It's terrible that we have to do negative instance samplings. One naive way is for each user we randomly select k candidates as negative instance. However, its performance is not optimal. In fact, we need to provide some strong negative candidates which are not easy to classify. To this end, we designed an iterative negative sampling method, which is shown in algorithm 1. Suppose we already have a weak classification models. In each iteration, we select some top training instances which are incorrectly predicted by the weak model. This idea is the same to idea boosting. The comparisons of random instance selection and our iterative negative sampling is shown in this table. We can see that our algorithm clearly improves the model. We compare the performance of several models, including gradient boosting, decision trees, logistic regression, and neural networks and SVMs with linear curves. Among these classifiers, gradient boosting decision tree is the best one. A golden rule for achieving top ranking in data mining competitions is that we need to train various models and make ensemble. However, it is usually time-consuming to find an optimal way to ensemble. We didn't join the competition until the last week before the end of the competition, so we proposed a simple but turned out to be efficient way to ensemble. For the training data, we trained two models, logistic regression and gradient boosted decision trees. We use logistic regression model to select top 100 candidates for each user in the test set. After these steps, we can get a relatively smaller test set length. We use the gradient boosting decision tree model to make prediction on this smaller test set. This table shows that our simple ensemble approach greatly improves the accuracy of the prediction. The summations are evaluated by the F1 score, which is a trade-off between recall and precision. And we don't need to submit too many instances in order to achieve a peak F1 score. We use algorithm 2 to select top instance for submission. Basically, we want to submit top n instance. On the other hand, in these top n predictions, if for some users their prediction number is less than k, we consider to complete his top k prediction on the premise that their top k prediction is not very far away from the global top n predictions. Finally, we submit about 10,000 instances. We end up with ranked seconds in the leaderboard. Actually, the top 3 teams' scores are quite close. During the competition, we have tried dozens of ideas, but only a few of them works. The most impressive lesson we got is that we need to keep learning and responding from failures. To summarize, we found 3 useful components which made our model a little special: comprehensive feature engineering, negative samplings, and model selections. In the future, we plan to try learning to rank methods. This is because in the past, similar projects such as CIKM2015, learning to rank model demonstrates a better performance than binary classifications, and our submission algorithms are also to some extent similar to the learning to rank frameworks, which indicates the superior of learning to rank model. Okay, that's all I have. I hope I made the presentation clear. If not, you are welcome to connect me through my emails. At last, thank you for listening, and thanks the organizers for the great contest.